So, talking about latent factor recommender systems. The main idea of the latent factor recommender systems is that we will think of recommendations as an optimization problem. And the way we think of this as an optimization problem is that we think of recommendations as rating prediction. And then the optimization is that we want to find the method that gives us best rating predictions. So here's the global idea. The global idea or the goal is that we want to make good recommendations. The way we talked about the goodness of recommendations was using the root mean squared error, right? The idea is the smaller the root mean squared error of our recommender systems, the better the recommendations. Of course, what we would really want is that we would want to make good recommendations on items that people haven't yet seen, right? Basically, we want to predict in the future what people are going to like. Of course, we cannot really do this because we are not prophets. We don't know the future. So what we will kind of have to be satisfied with is the second point, right? We want to build a system that is able to predict the ratings that we already have well. In a sense, what do I mean by this is that we have our rating matrix, we will hide a few entries from it, and our goal will be to predict those ratings well. And hopefully, by doing that, if we then go and take this recommender system and release it, let's say live on the Netflix website, that system would also work well for the truly unknown ratings. Right? So the way we think about rating prediction for recommender systems is the following. We have our rating matrix R with users and movies, and our goal is that we want to make a system that predicts well the hidden ratings. What do I mean by this is that we will take some of the ratings from our utility matrix, and we will hide them, and our goal will be to build a system that for each of these cells kind of exactly predicts the value that is in that cell. Right? So we want to kind of hide the known things and then predict it. And the idea is that the system that is able to make the small root mean square error between the true ratings and the predicted one, that's the best system we have. Now, how do we approach the rating prediction problem? The way we will approach this is through matrix factorization. And this is why these models are called latent factor models, because we basically go and factorize the matrix. In some sense, we will be applying singular value decomposition or a version of singular value decomposition to the Netflix utility matrix. And the way we will do this is the following. So we are given our matrix R, and we will try to represent our matrix R as a product of two matrices, matrix Q and matrix P, right? So we will say that matrix R equals matrix Q times matrix P. The difference here is the following, right? So if you think of the matrix R as items to users or movies to users, then we can think of matrices P and Q as kind of thin and very long matrices, right? So for example, we will think of matrix Q to have the one row per item, and it will have k columns or k factors, where k is some value that we will decide. And usually we can think of this k as maybe 100, 200, 300, right? So something much smaller than what is the total number of users in our data set. And similarly, matrix P will be this kind of also very thin matrix where we have one column per user, and it has k row, where again k is this parameter that we choose, right? So for now, let's just assume that we can approximate our matrix R simply as a product of two thin or narrow matrices, Q and P. Okay? There is one slight issue that R really has missing or unknown entries, right? That there are these regions of matrix R that are all unknown, but for now, let's ignore that. Okay? So all we did is we kind of mathematically assumed that we can take R and factorize it into this as a product of these two matrices. Okay? What this really does to the data is the following. The way we can think of every row of our matrix Q or every column of our matrix P is that basically every item and every user gets mapped into this three-dimensional space, right? So we can think of every row or a column of P simply as a let's say three-dimensional representation of a given user or of a given movie. right? So what this really means is that we took this big utility matrix R, and now we took all the movies and all the users and mapped them into this, as I showed in the previous slide, in this kind of three-dimensional space. And this is why, and this axis of this latent subspace are called factors, right? So kind of the idea is that now movies and also users get mapped into this space, where basically this axis that we find here are the axis of variation, right? So maybe just hypothetically, imagine that what our factorization would discover is that we have our space has two main axes of variation. There are movies that are geared towards females, and there are kind of the guys' movies, and then there are, you know, the serious movies, and then there are funny movies, right? And now every user is a data point somewhere in this space, and also every movie is a data point in this space, right? And some users or movies are closer together than some other pairs of movies and users, right? So that's kind of what latent factor recommender system is doing. In some sense, it's finding this low-dimensional representation of users and movies such that kind of people that like those movies are close together with each other. So now, assuming that we can do this, take the matrix R and represent it as matrix P and Q, the question is, how do we estimate the missing rating of the matrix R, right? So for example, what is our prediction for a given cell of the matrix R? That is very easy. All we have to do is to say, aha, we are making a prediction for user number 4 and item number 2. So all this means is we have to take the corresponding row from the matrix Q and the corresponding column from matrix P. And now what we do is basically we dot product these two vectors with each other, right? So basically we do a weighted combination or an inner product between these two vectors. And if we were to go and multiply these two vectors together, the prediction we would get is 2.4, right? So our prediction about user 4 liking movie number 2, basically predicting the rating, would be 2.4. So what this really does, as I mentioned before, is that the whole method discovers these latent factors or these latent dimensions in which the movies can be mapped according to the matrix Q, and also people can be mapped into the same space according to the matrix P, right? So what would happen under this view is that users are points in this space, movies are points in this space, and then the prediction basically means is what users are close to what movies. Of course, this also very nicely relates to the singular value decomposition that we already know about. So let me remind you about the SVD. What SVD does, right? In that lecture, we said, let's assume we have some matrix A, and we want to represent this matrix as a product of three matrices, U, sigma, and V transpose, right? And we called the matrix U to be the matrix of left singular vectors. Matrix sigma is the diagonal matrix of singular values, and the matrix V is the matrix of right singular vectors, right? And we showed in that lecture that this can be done for any matrix and so on and so forth, right? So in some sense, SVD is already doing what we want, right? So if we take our matrix R and perform SVD of it, then we could simply take the matrix U and call it as matrix Q, and we could take the product of sigma times V transpose and call this part our P transpose, right? So in some sense, SVD is already kind of doing, or it seems it's doing what we want, right? So that R equals Q times P transpose, and SVD is able to compute this for us. However, even though it seems we are done, we are not really done. Before I tell you why we are not really done, let me tell you kind of one more good thing that kind of comes from SVD for free. So one thing that we know about SVD is that SVD gives us minimum reconstruction error, right? SVD gives us the minimum sum of squared errors between the true value in an entry of the matrix versus the approximated value of that entry in the matrix, right? This is the Aij is the entry in the data matrix, and sigma U times sigma times V transpose is basically the value, the approximation coming from SVD. And we already know that SVD gives us, in some sense, is the solution to this minimization problem, right? Finding the three matrices such that the approximation is as good as possible. What is there to note? First thing to note is that this sum of squared errors is basically the same as the root mean squared error, or is related to the root mean squared error, right? If the sum of squared errors is small, the root mean square error will also be small. Why? Because the two are monotonically related, right? Root mean square error is nothing else than sum of squared errors, the square root of that, and then multiplied by some constant, 1 over the number of data points, right? What this basically means is that SVD is already minimizing the root mean square error, right? Actually, SVD is able to find the product, the three matrices that give us the best possible root mean square error, right? Which is great. So it seems SVD is really the right thing to do in this case. However, there is one slight complication, and this I write here, right? The complication is that SVD assumes that the matrix A has all the entries given, right? The summation here, ij over A, goes over all the entries of matrix A, right? The matrix A is kind of completely filled in, but our matrix R is not filled in, right? Most of the matrix is empty, meaning for most part of that matrix, we don't know how much does a given user like a given movie. So if we were just to ignore those parts, basically what that would mean is that no rating is interpreted as 0 rating, which is clearly wrong in our case, right? So this really means that R has missing entries and SVD is not able to accurately account for the missing entries. So we have to kind of be a bit smarter. We have to think of the SVD, but change it a bit. So the way we change the SVD is the following, right? What we know is that SVD isn't defined when for the entries that are missing. So what we need to do is we will have to use specialized methods to find P and Q. In particular, we will solve the following optimization problem, right? Recommendations as optimizations, in a sense that we want to find matrices P and Q that minimize the sum of squared errors, but now the errors, right? We only go over the entries of matrix R, meaning we only go over the yellow entries of matrix R and not all the cells of the matrix, right? And what this is saying is the following, right? So I want to find matrices P and Q such that when I sum over all the known ratings, the value of that rating minus my predicted rating, that difference squared is as small as possible, right? So now the game is it's very clear. I want to find matrices P and Q that minimize this expression, that are basically best able to predict known ratings in my matrix R. And I hope that by being able to find such matrices P and Q, I'll be also able to predict well the ratings that I don't even know, so the unknown ratings. A few things to note here. First is the difference between SVD is that here for P and Q are kind of completely arbitrary, so we don't require that columns are orthonormal, meaning that vectors are unit length and they are orthogonal to each other. As I mentioned before, we can think of matrices P and Q as mappings of users and mappings of movies into this low-dimensional space. And what is interesting is that if there was kind of one big breakthrough in the Netflix challenge, then these latent factor recommender systems were the most widely used and also the most successful method in the whole competition. So what we will do next now is we will learn how do we actually go and solve this latent factor optimization problem. So the equation I have written here.